Okay, this video is just going to be about how to start some of these problems in Chapter 7. I think that's part of the issue sometimes is just like, what do I even do to get started? So we're just going to go through them one by one. I'm not going to go all the way to the answer, but I'm just going to show you how to get started. Just adjust this camera. Okay, so 13, Illusion its rider, total mass at 85 kilograms, emerge from a downhill track onto a horizontal straight track. So I'll just get some paper to work on over here. And they have an initial speed and they have a force that slows them down with an acceleration. So you basically have something that's got some initial speed, 37 meters per second. It's going to slow them down to a stop, and we are going to have to find the distance and the force and the work. So however far they go, this is going to be v equals 0. This distance is kind of unknown. Let's scooch this up a little bit. And what we do know is that the acceleration is 2 meters per second squared. So I know I keep saying you should try energy before you try forces, but I think this one will work out with forces, except for when you're trying to find the work, then you'll have to figure out energy. But even that one is actually pretty easy to do just from energy considerations. But I think it can go either way. So just to think about what force is required, we just have F equals ma, so that's pretty easy to do. What distance do they travel? I think it's probably easy just to use our v squared is v0 squared plus 2a delta x, realizing that their velocity at the end is 0 and you have an initial velocity. That's pretty easy to do. The work can be done a couple different ways. Work is force times distance. So if you've already figured out the distance, then the work would just be force times distance. That would be one way to do it. You could also do that work is change in kinetic energy. So you could do 1/2 mv final squared minus 1/2 mv initial squared. So either of those things will get you the work. Then next time you just have a different acceleration. So that should be pretty easy to do for parts D, E, and F. Okay, so that's just how to start problem 13. Like I said, I'm not going to solve them for you. I'm just going to show you how to start them. Okay, so now we move on to 17. Let's see. Helicopter lifts a 72 kilogram astronaut 15 meters vertically from the ocean by the means of a cable. The astronaut has an acceleration of g/10. How much work is done on the astronaut by the force from the helicopter and by the gravitational force? And then just before she reaches the helicopter, what are her speed, her kinetic energy and speed? So once again, we could kind of do this with the forces thing. So we just have an object, it's being moved up, and its distance is 15 meters. The acceleration is g/10. So, okay, that's kind of an interesting way to do it. We have a mass, 72 kilograms, and great. So how much work is done on her by the force? So we can do work, I think it says the acceleration is g/10. So we can do a couple different things, but I think using work as force times distance would probably be the easiest way to do it. We could also do work as change in kinetic energy. So if we have done by the astronaut, I guess we don't really know her initial velocity, so this might be a little hard to do, but we could find her change in velocity from her acceleration, and that would be in one way to do it, but I think that's easier to just do work equals force times distance. And how do we find this force over here? Well, her acceleration is g/10, so let's draw a free body diagram just to see what's going on here. So we've got mg going down, and we've got the force from the helicopter pulling her up, and don't forget we need to do net force equals mass times acceleration. So we'll pick this one as the positive direction. So we've got F minus mg equals ma. We also know that the a is g/10. So that's going to equal m times g/10. And I'm looking for what this force is. So I can just add this to the other side. And I could do F equals mg/10 plus mg, which I guess is like 1 1/10 mg, something like that. Anyway, so you have the force, plug in some numbers for the force. Once you have the force, you could do work equals force times distance. As far as the work done by the gravitational force, well, there's the gravitational force. So that's pretty easy. Just before she reaches the helicopter, what's her kinetic energy and speed? I guess it doesn't say it, but I guess we can just assume that her initial velocity is 0 because she's being lifted from the ocean, so that's fine. So I guess we could have done this work equals change in kinetic energy. But what's her kinetic energy? Well, okay, so now we can do this because now we have we know the work that's done. Actually, so what we need to do to think about this is what's kind of the net work that's done, and that's going to be the work that was done by the force minus the work that was done by gravity. So there's kind of like a net value for the work because gravity is doing some work and this force is doing some work. So the overall results of those will let you do the change in kinetic energy. So, and then you can find her speed from the change in kinetic energy, remembering that kinetic energy is 1/2 mv squared. So that's kind of how to start it out. Once again, I'm not showing you the solution completely, but I'm just showing you how to start it out. Okay, so 19 over here, and it says a block of ice. So it's important to read this. It actually slides down a ramp. The angle's 50 degrees, while an ice worker pulls up with a force that has a magnitude of 50 newtons. This to slide up the ramp. So it's going down the ramp, but this person is pulling it up, which is kind of strange to think about. So it must be that this force is not enough to lift it up, that it's actually going down the ramp. And its kinetic energy increases by 80 joules. So it's speeding up as it's going down the ramp. How much greater would its kinetic energy have been if the rope had not been attached to the block? Increases by 80 joules. Okay, so basically what it's really asking is like, how much work does this force do? Because if the force weren't there, then it would be more kinetic energy would be going to the block. But because this force is here, less kinetic energy goes to the block. I'm not sure we need this 80 joules of kinetic energy. How much greater would its kinetic energy have been? I don't think we actually need that. I'm just going to pop over and look at kind of my more full solution here for a sec, because I don't think we need that 80 joules of kinetic energy, except if we're just like kind of adding to it in the end. So yeah, I don't think we actually need that 80 joules. So here's the idea. We're just trying to figure out how much work did this force do in lifting up this block. And but it's actually pretty easy to do because we're just kind of dealing with a force and a distance, and that's it. I mean, I don't really know how much more complicated it can be, but I think the angle is kind of irrelevant because we know what the force is and we know what the distance is. So as far as I'm concerned, you know, work equals force times distance. That's how much work this force does. And if that work weren't there, it would have had more kinetic energy. So I don't know why it's a 2-dot problem. It doesn't seem like it's that hard, except that the setup is kind of funky. Like you don't really need the angle because it's already telling us this force. The force and the distance are really in opposite directions. So maybe if we had cosine of the angle in there and then the angle is 180 degrees, right? Because the force is this way and the distance is that way, but I don't really see why this is a 2-dot problem. It seems pretty easy. Okay, maybe just the setup is confusing, and that's why it's a 2-dot problem. Okay, so let's go through another one. Yeah, this is another example of like a problem that just seems so hard to look at. It's like, wow, there's a lot going on there, but if you kind of know the trick for it, this focus is a little bit funny. Let's see if I can fix that. I guess that's okay. So this says a constant force right here is applied. We have the magnitude of the force, 82 newtons. It's a 3-kilogram shoebox. This angle right there is 53 degrees, causing the box to move up the ramp, frictionless ramp, at a constant speed. That's important to note. And how much work is done on the box by this when the box is moved through a vertical distance of this. So this is actually pretty interesting. When I was first looking at this problem, I thought about it in a hard way, and then it turns out to be there's a really simple way to do it. So what's the hard way to do it? Well, the hard way to do it is to break down this force here into components. One component that's going along this way, and one component, I guess that was a little bit too far to draw. So along the distance, and one component that's going this way, figuring that this angle right there is the same as like this angle right there. So you can figure out your cosines and your sines. And then the problem is we need to know this distance from there to there. But what we really only know is the vertical distance that it goes. So we know this distance from there to there. The height is 0.15 meters. So I could figure this one out because I know, I guess it's like from here to there, sorry. It's not from way down there. It's from here up to there is the height. So I could figure it out using some trig because I know the angle and so forth. And you can get in there and you can do it. I think it's just a little bit tricky. But the key here is if it's moving at a constant speed, then that means that the net work has to be 0 because the change in kinetic energy is 0. So I can't have any work overall that's done. So if I have a force that's acting this way, it's got to be counteracted by, not the force doesn't have to be counteracted, but the work done by this force that's pulling it up the ramp is going to be exactly equal to the negative of the work that's done by gravity. So really, if we think about this, the work that's done by the force has to equal the work that's done by gravity. And the work that's done by gravity is really, really easy, because if I have something and it moves up a particular height, then the work is just the force times the distance, and that's just m times g times the distance. And I know this distance right there, that's just the h, oops, right there. So this is just really m times g times h. And those of you who did physics before will recognize that this is just the formula for potential energy. So this is the work done by gravity. The work done by gravity, and so that's it. So I didn't need the angle, I didn't even need the force. I need the mass, but I didn't need any of that other stuff. All I needed was the vertical height that it went, and that was going to be it. So that's actually turns out to be a pretty easy problem. But I can see why it's a 2-dot problem, because you can get sent on like a wild goose chase, and it would be sort of tricky that way. Okay, moving right along. So 27 is a spring problem. Let's skip that one for now. 29, a bunch of these we just haven't done yet. This is a different type of problem as well, with a work and a distance. So let's not do 29 yet. 31 is a variable force problem, so let's skip that one for now. This is a variable force problem. We'll talk about that in class. This is a variable force problem. We'll talk about that in class. Let's see about 42. The diagram's over. Okay, cool. So we can do 42 right now. Once again, I feel like the focus is just kind of off here. But anyway, you can look along in your book to see what these problems are. So 42 shows a cord. Oh, this is a 3-dot problem. Ooh, all right, cool. A cord attached to a cart that can slide along a frictionless rail along an x-axis. The left end of the cord is pulled by a pulley. Okay, great. So the cart moves from here to there. This from x equals 1 to 3. Okay, so this is a distance of 2 meters right there. And during the move, the tension in the cord is a constant. Okay, that's nice. Constant 25 newtons. What is the change in the kinetic energy of the cart during the move? Okay. I don't know why. Oh, a cord at a height of 1.2 meters. Okay, 1.2 meters right there. I don't know why that's necessarily going to be relevant. What is the change in the kinetic energy of the cart? Well, what we know, of course, is we're going to do work equals the change in kinetic energy. So I'm really just finding the work. I guess I could figure out how fast the cart increased its speed by some Newton's laws type of thing, but I think energy is going to be way better in this standpoint than Newton's laws. The problem with Newton's laws is that, yeah, I have a tension here, but the angle keeps changing, and so the force on this block also the force on the block in this direction kind of keeps changing as well. But the work, interestingly enough, is only going to be based upon, so here's the key to this problem. So the cord is pulling in this direction, and if we can figure out how much the cord moved in this direction, then we can figure out how much force times distance it is, because we already know that this tension it's given is 25 newtons. So if we can find out this distance that the cord moves, it doesn't even matter if it's this distance. Wherever the cord is moving, we can just figure out how much distance the cord moved, and then we can figure out what the work is, because the work is just going to be force times the distance. So if we think about this situation, maybe we can kind of draw, here's a before and after picture. So kind of drawing triangles here, like here's x2, here's x1, and we have this, and then we have the cord kind of going like that. And then in the next picture, I've got x2 and x1, and then the chord is kind of going like that. So if I can find out how much distance the chord changed, then I can figure out this problem pretty easily. So I guess your task, and I'm just going to set you up with this and have you figure it out, is how much chord actually got pulled through. So when the chord is here, it's got a certain amount of distance, and then when it's here, maybe I'll draw it over here, it's got less distance. So what's the difference in this distance versus this distance? And it's just like a little geometry problem, right? So here's the chord as it's already stretched out, and then here's this chord right there. So what's the difference between that distance and that distance? So just try it out like a little geometry problem. I think it should be fine. Okay, moving right along. This is kind of a lot, but hopefully this is helpful for you all. 43. So I should have printed these out bigger maybe, but it says a force of 5 newtons acts on a 15 kilogram body at rest. Compute the work done by the force in the first, second, third seconds and the instantaneous power. Okay, so I'm assuming this is just like a force that's pulling something along a frictionless surface, even though it doesn't really say it. It's a 5 Newton force, and it's 15 kilograms, and I want to find the work done in the first second. Not the meters, but it's in the first, the second, and the third seconds. So it's kind of a time thing here. I think probably this time, since we don't have a distance, we can't really do work equals force times distance unless we figure out what that distance is, which wouldn't be too hard to do, but I think maybe it's better just to do work is the change in kinetic energy. If it starts from rest, so V0 is 0 over here. And yeah, if we can find out what its speed is at the end of this 5 meters, that's actually, oh no, we don't have it. Oh, it's at the end of a second. Oh, that's actually really easy then. Okay, cool. So here's the setup, because we can do just force is mass times acceleration, or acceleration is force over mass. So I know the force, I know the mass, so I could find a value for the acceleration. So that's not so hard to do, because I know the force and the mass. Once I have an acceleration, we can just remember that velocity is acceleration times time plus initial velocity, but we don't have it. So I could find the velocity at a particular time, plug in 1 second, 2 seconds, 3 seconds, and then I can find the kinetic energy in that time from the velocity 1/2 mv squared, right? So actually, it might even be nice to, since we have to do this 3 times, it might even be nice to just kind of come up with a formula for it with variables first. So let's come over here. So A is F over M, V is A times T, so I can write V is, sticking that there, F over M times T, right? F over M times T right there. And then the kinetic energy is 1/2 mv squared. So I can do the kinetic energy is 1/2 m times this thing, F over M, times T squared. Okay, so that's just going to give me F squared T squared over 2m. So that's what the kinetic energy is going to be. So now I can just plug it in for the time of 1 second, the time of 2 seconds, and the time of 3 seconds. So that's easy. Force is given, mass is given. Cool, that's kinetic energy. Remember, the kinetic energy is the work. It's really changing kinetic energy, but we have 0 initial velocity, so that's really helpful. Let's see, part D says the instantaneous power due to the force at the end of the, okay, hold on a minute here. The instantaneous power due to the force at the end of the 3rd second. Oh, okay, well, I think that there's various things to do for power, but power is also going to be force times velocity as long as we have a constant force here, which we do. So if I can figure out the velocity at the end of the 3rd second, which I already know, and multiply it times the force, then we should be good. That's going to be the power. You might be thinking, if you see instantaneous power, you might be thinking, oh, I got to take a derivative somewhere, but sometimes you don't really have to take a derivative. That's why we have this formula. It's like the derivative is kind of built into the velocity in some sense. Okay, so that was 43. Let's look at 45. 100 kilogram block pulled at a constant speed. That's nice. 5 meters per second along a horizontal floor by an applied force. What is the rate at which the force does work on the block? Okay, so let's just draw a picture here. Got this, constant speed, mass is 100 kilograms, oops, where is it? The applied force. So we have a force this way, and we have this angle, which is 37 degrees. The force is 122 newtons. Oops. What is the rate at which the force does work on the block? Okay, so I mean, I think that this is just going to be a pretty simple problem with energy and work and power. Let's see. So if we have, if it's a constant force, let's think about how we might want to do this here. The rate at which does work on the block. Oh, this is actually, I'm wondering if there's a way we can do this without thinking about it in terms of an integral. What I'm thinking here is we have power is work over time. And so that's kind of what we're going for here. And so I'm wondering about this problem. Let me come back to this problem and see if we can figure this out with maybe doing it a different way. So hang on to your horses for 45. It shouldn't be that hard of a problem, but I think, yeah, I think it might be a little bit tricky. So let's hang on to that one. 49. Fully loaded, slowly moving cab has a total of mass required to travel upward 54 meters in 3 minutes, starting and ending at rest. Okay, that's nice. The elevator's counterweight has a mass of 950 kilograms. The elevator motor must help. What is the average power required? Okay, so we got an elevator here, and then it's like going up over a pulley, and then there's like a counterweight over here. And this is 1,200 kilograms, and this is 950 kilograms, and then this thing has to go up a distance of 54 meters in 3 minutes. Okay, what is the average power required? Okay, so we have a time right here. So we're going to do power is work over time. So really we're just trying to figure out how much work is done by the motor. Okay, cool. So I guess the idea here is if the counterweight were 1,200 kilograms, it wouldn't require any work to move this thing up, right? Because this would move up and this would move down, and they would kind of balance each other out. So it's sort of like how much work, like this thing moving down is going to take a little bit of work away, and this thing moving up is going to take a little work away. So I think maybe how we could set this up is thinking that if it starts and ends at rest, then the net work has to be 0. The overall work has to be 0 because I'm starting and ending at rest. So maybe it's good to think about it as like the work done by the elevator plus the work done by the counterweight plus the work done by the motor. And then we can figure out what this is kind of based upon these things. So if I can figure out the work, it's really like the work that gravity does on the elevator and the work that gravity does on the counterweight. So this actually shouldn't be too hard to do. Oh, there goes my lights. Hold on. There we go. Okay, now I have to adjust this brightness here. Let's go. Okay, that's better. So this is just work done by gravity on the elevator, work done by gravity on the counterweight, and then the motor work has to take into account over here. So this one, since this thing's going up, it's going in a direction opposite to gravity, so this one will kind of be negative and this one will be positive, and then this one will have to take the place of it. So the work done by the elevator is going to be the mass of the elevator times gravity times this distance, and that's going to be negative work. So this is the work done by gravity on the elevator, and then the work done by the counterweight is going to be the mass of the counterweight times gravity times the distance, and then here's, I guess, plus the work done by the motor has to equal 0. So I'll just start you out with that, and then once you get how much work the motor does, then you can just divide it by time to do the power. So that one's actually not that hard. Okay, very long video. Hopefully it was helpful for you all to just get going on some of these problems.